So if we take a look at it, the arguments we actually give to the kernel are actual registers. Okay? So all we have to do if we want to emulate a switch to structure, call VM86 or VM86 old. Actually, VM86 old is nowadays calling VM86 itself. And this is going to emulate a switch to virtual mode. So you may be thinking, okay, this is entirely emulated. So what's the point? We won't get access to hardware, right? Not really. The good news is the fact it's being emulated means we can trigger it from inside a virtual machine. So we can still program using rolled interruptions. And if you think at it, how do you emulate, let's say, writing to a disk from inside a virtual machine, or display a pixel? You actually do it. So if you want to emulate writing to a disk, you actually do write to the disk. It goes through several layers of emulation, simulation, whatever, but we don't care. We still get access to the hardware. And we can program the old school way. So what we just got this way is a bare metal, possibly virtualized hardware interface. So the practical use of this is obviously writing a fuzzer, which is as exhaustive as possible. So we've seen trying every value of every register which can be used as an input would mean trying around 10 power 19 operations. Okay, I can't afford that. I don't have a huge cloud to do this. But if you guys have the necessary power and you want to share, feel free to ping me. But what we can do is fuzz ether plans. So for instance, we for a given value of EAX, which is a particular function for a particular interrupt, we can try all the values of CX, DX, DX. So let's have a look at the interrupt vector table inside my machine. Can you go up a bit? I can try to. Okay, so the interrupt vector table inside Linux is accessible through /devmem, okay, which is a mapping of the physical memory, and it's typically located inside, as we've seen when the CPU gives control to the BIOS sets it up at the very first stage of the physical memory. So what we have to do is read from devmem the interrupt vector table and display for each particular interrupt what is the ender of this particular interrupt. So the input is reasonable. I'm not printing the null ones. Okay? So what we see is that some of them are actually replications. Okay? Okay, all of this, for instance. So if you try to call interruption 2F, or if you try to call interruption 2D, for let's say, your call is gonna end up calling the same ender. When you have that many interruptions rerouting to the very same ender, it just means there is no ender at this particular place. So if we try to enumerate those which are actually usable, so either unique or not too different, or existing with not too many repetitions, it's very easy to enumerate the interruptions that are actually actual. So for instance, interruption 3, which very much exists, okay, it's a SIG trap. Well, it's a trap, which is called when you get a SIG trap. Interruption 4 is redirecting to it, but most probably it doesn't matter. I mean, you could actually use the fourth one instead of the third one, and it will give you the same result. So let's go for the how to say demo part, whatever results. So all we want is hypervised bug. Keep in mind that when we're talking about that low-level bugs, many times one bug will give you by itself a root shell. You might need to combine a few of them. This is what happened with the bug of Julien Tinez, right? You had one in the ending of the page, and you had a second one to trigger it. So this is typically what happens when we try to fuzz VirtualBox. Okay, so this is the hypervisor crashing, and this is what the screen looked like after running a fuzzer. You can clap your hands. Thank you. So this is also VirtualBox dying with a scary message. We got more bugs with different virtualization systems, but typically they look like guess only. I'm still writing this, I'm still putting this virtual PC1 on my slide because it took me 24 hours to get one bug. And most typically it's about only the guest operator, the guest VM, but still. And Parallels, which is the one from the virtualization environment from Apple. What's interesting here is the value of the IP, okay, which is obviously super wrong. Looks like a 16-bit address.